here I have some data, just some experimental data that I've just kind of made up. And we want to perform a regression on this to try and find out what the relationship is between x and y. First of all, let's have a quick look at what the data looks like. If I go into insert, and here we go. So, as we can see, it's quite clearly non-linear. And actually, what we might want to do is use a least squared fittings model, least squared fittings, to try and find a relationship between x and y. And one way we can do this is, first of all, linearizing this. So if we take ln of x and ln of y, so I'm just going to pop that in now. We want x, and then I'm just going to drag this down and drag this over here. Excellent. Now, if we plot these, instead we should hopefully see a linear relationship. All we know from our data is that the numbers should follow this relationship, that y equals a times x to the power of b. So we have two coefficients a and b, and hopefully by linearizing them we can find what those coefficients are. As of course, ln of y will be equal to b times ln of x plus a. Sorry, ln of a. So hopefully we'll be able to, by linearizing this, we'll find these coefficients as the gradient b and the intercept a. So let's quickly plot these. Once again, just going to a scatter plot. Excellent, that looks pretty linear. Fantastic. Okay, so Excel actually has some built-in functions to perform regressions on data to try and find what the relationship is. And the easiest way is to just add a trend line. And as you can see, we get this dialog box that comes up, and we have exponential, linear, logarithmic, yada, 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 yada. But we want to use a linear least squared fitting technique. So we're going to stick with linear. We know that the intercept isn't 0, so, well, we don't know what the intercept is of course, because it's going to be ln a, so we'll leave that blank. But a display equation on chart, we want this. So we can close, and there we go. We have the equation of this line. So b is, what's that, 3.9898, and ln of a is 3.756, blah, 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 blah. So if we pop in for b, this should be 3 point, let's just call it 99. That'd be easy enough. And that's pretty close. Actually, the answer is 4, but I've added some noise to these, so it won't be exactly 4. And now if we take ln of a, so what we need to do is reverse that. So we're going to take the exponential of 3.7596. And what do we get? 42.93. The answer we're looking for is actually 42. So this value is close enough, but as you can see, it's not spot on. And this comes from converting into a logarithmic scale and then converting back again. Now, you may say, well, what's the point in us doing this if it's not going to give us an answer that's, spot on for our intercept? Well, of course, with this, we can try and interpolate in between these points to try and make up any extra data here. So for an interpolation, this is a great technique to use. So we'll pop in, 42.93, and as we see, we're a little bit off. Actually, that isn't our answer. Okay, so this is one way to do things, as I say, by linearizing, and we can actually use this technique. Excel has some other capabilities to calculate these regressions, and we're going to use the data analysis toolpack and the solver add-ins. Now, in your version of Excel, you might find this Excel options here at the side, but for I believe this is 2007, the option is here. But this should all look the same, and there's this option here for add-ins. Now there's a whole list of add-ins. And what we can do, we have those that are inactive and those that are active. All we need to do is manage our Excel add-ins, go, and then we can select which add-ins we'd like. Now, if you haven't got these installed, there'll just be a prompt to ask you to install them. But what we're going to use is this analysis toolpack and this solver add-in here. This VBA version is for Visual Basic Advanced, so it's a programming language that can be used with Excel. So we're not going to worry about that, but that might be handy for anyone who knows how to use Visual Basic. Okay, so let's copy this data. Let's just let's just copy the whole lot. Copy, and I'll pop this here. Paste. Okay, so let's see what answer it will give us for this one. So all I need to do for me, I go into data, I believe. There we go, data, and then this data analysis tab here. Any extra add-ins tend to come up in their own little box. So data analysis, and as we can see, there are loads of different options. We have F-tests, we have Fourier analysis, which is incredibly useful. We have loads of things, but what we're going to use is this regression function here. So we hit OK, and a dialog box comes up. Input our Y range, and we're going to use our ln once again, so we can use a linear least squared fitting, and down this way. There we go. So that is our Y range and our X range. Now it spews out a lot of information, so we're going to put it into a new worksheet, but we'd like to see the residuals, we'd like to see a residual plot, and also a line flip plot as well. So if I hit that, here we go, and it's crunched through everything, and there we have it. So our coefficients are 3.759 blah 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 and 3.989 blah 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 blah. If we let's quickly copy this and pop it into this sheet, hopefully we'll be able to compare our two answers. So in this case, our b value, our gradient, in this case our x variable, sorry, I'll expand that out, our x variable was 3.9898 rounding up, and this seems pretty close enough, 3.9898 if you're rounding up. And for this one as well, 3.7596, well, that's pretty much it. It's just that on this one it's been rounded up. So excellent. It does pretty much the same thing, but as you can see, it gives you a lot more functionality. We have, let's get rid of this one. As we see, it has a line plot. It's essentially put our model, this predicted y, on top of the y, and actually they're probably about the same size, so you can't see them. Let's make them a little bit smaller, size 2, and now they're just sort of, as you can see, they're just red dots on top of, red squares on top of blue diamonds. So yeah, a pretty good fit in that respect. And we have residuals here as well. But remember, this is only for our linear scale, so for our log of x and log of y. So these residuals don't compare to the model compared to our real data. And the same for this as well. These residuals, as I say, they're for the linear model when we've linearized, and not the a times x to the power b. It's the linear version, which was this one here, ln of y plus yada 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 yada. So some other helpful things, p-values and all this malarkey. If you don't know what they are, then I wouldn't bother. Just go through it the old-fashioned way, and at least you'll be able to see what you're doing, and you'll have a clearer view of what you're doing. Now, finally, we have the solver add-in, and what I'm going to do is I'm just going to quickly copy this, and hopefully paste it in here. Excellent. So we have our data. Now I'm going to take our values from our earlier estimates. So let's just copy this and pop it in here. Paste. And we are going to essentially manually try and find these coefficients using a non-linear method, using the solver add-in. So our model for y is essentially working, so using these coefficients, what does y come out with this x? Now I have this code already worked out somewhere else, so I'm quickly just going to cheat a bit and copy and paste. Okay, so pop that in here. So I've said this constant times, so that's a times, and in this bracket it's x, this b4 to the power of this here. If anyone who's not familiar with what these dollar signs mean, I can show you. So if we drag this equation into all these other cells, we can see that it goes from B4 to B5 to B6, yada yada, B7, all the way down. But you can see that these values stay exactly the same. If I was to take these out, when I drag that down, they become C2, C3, C4, C5, and it wouldn't be referencing these anymore, which obviously isn't any help to us. So for our residuals, what we would like is our model times, our model minus our real value. Or we can do it the other way around, in fact. What we can do is we can say equals our data minus our predicted value. And as you can see, we have what are our residuals. So these are the difference between the two values, between the model and our data. And as you can see, actually down here, they get quite significant. And as we know that least squared fittings essentially minimizes the sum of these residuals squared. So if I take the absolute of this number, how if I put in equals? So equals the absolute of this number squared. So to the power of 2. And I'll drag that down to populate all of these. And so this square here is going to be the sum of all those residuals squared. So I'll just pop that there, finish that off, and then we have it. So what our solver is going to do is minimize this number by changing coefficients A and B. And of course we could sit here and do this and maybe go up half a step or go down half a step and try and minimize these, but of course this is what computers are for. They can do all the brunt of the work for us. So we've set our target cell, which is this one here, and we can either maximize, minimize, or set to the value of whatever. In this case we want to minimize that number. And so we want to minimize this value by changing A and B. We could set constraints, so we could say that perhaps A and B have to be integers or whatever. Of course, if we just have some random data, we don't know if this is the case. So I'm just going to leave this blank. And here we go. So it's solved. It's solved and it's minimized these the best it can. Sometimes this may come up with an error if it can't satisfy a condition. So if we went back and then used the solver again, and let's say we said, okay, we want you to get to a value of 0, and we solve that again, and then it's saying solver could not find a feasible solution, but it has tried its best and essentially got down to the smallest number it can. So let's try that one more time. So we're going to go to minimum, solve. There we go. So now we have two values for A and B, and you can see this is much closer to our real answer. We have 42 and 4. And if you were to plot these against another, hopefully you would see, you can see our residuals have reduced quite massively as well compared to what they were before. If I can't undo, unfortunately, but yeah. So that is how you can perform regressions in Excel using the built-in trend line. You can use the analysis tool pack to bring up all sorts of data, including residuals. And for nonlinear functions, so this isn't using, doesn't quite use a least squared fittings model, but we've kind of forced it to here, and that's with the solver add-in there. Okay, I've been Andy. Thank you very much.